Isotopes are atoms of the same element which have the same number of protons but different numbers of neutrons. Therefore, isotopes of the same element have the same proton number but different neutron numbers. The name isotope is derived from the Greek word isos, meaning equal, and topos, meaning place. This refers to the fact that all isotopes of a particular element have the same position in the periodic table. Most elements have more than one isotope. To differentiate isotopes of the same elements, their neutron numbers are written after their names. For example, a carbon atom can occur naturally in three forms, namely carbon-12, carbon-13 and carbon-14. These carbon atoms have the same number of protons but different number of neutrons. These carbon atoms are called isotopes. Let us have a look at all the isotopes of hydrogen at a time. The simplest element, hydrogen, has 3 isotopes. Because of their importance, they have been given their own name and importance. Hydrogen-1 is referred to as protium. Protium has an atomic number 1 and mass number 1. This means that it has 1 proton, 1 electron and no neutron. The isotope hydrogen-2 is named as deuterium and is designated by symbol D. Natural hydrogen contains 1 deuterium atom for every 6,666 atoms of protium. Deuterium isotope of hydrogen has 1 neutron besides the proton. This means that its atomic number is 1 and mass number is 2. Because of the fact that deuterium is twice as heavy as protium, it is called as heavy hydrogen. Water containing deuterium is referred to as heavy water. 100 cubic centimeters of water has a mass of 110 grams. Hydrogen-3 isotope of hydrogen is referred to as tritium and is designated by symbol T. Natural hydrogen contains 1 tritium atom for every 10 to the power 16 protium atoms. The tritium nucleus is the heaviest of all hydrogen isotopes as it is made up of 1 proton and 2 neutrons and has atomic number of 1 and mass number of 3. Tritium is a radioactive isotope and it emits beta particles. Oxygen-17 has 8 protons, 8 electrons and 9 neutrons. Oxygen-18 has 8 protons, 8 electrons and 10 neutrons. Uranium-235 has 92 protons, 92 electrons and 143 neutrons. Its mass number is 235. Uranium-238 has 92 protons, 92 electrons and 146 neutrons. Its mass number is 146. Isotopes of the same element have same proton number. Hence, they share the same chemical properties. They have different masses and can be shown with the help of an experiment. Let us take a beam balance and place an atom of chlorine-35 at one end and an atom of hydrogen at the other end. Since hydrogen is equal to one atomic mass unit of one unified mass represented as U, we find that in order to balance the beam, 35 hydrogen atoms are needed. Mass of chlorine-35 isotope is 35 AMU. If we take a heavier chlorine-37 isotope, we find that 2 more atoms of hydrogen are to be added to balance the beam. So, the mass now is 37 AMU or 37U. Let us now learn about the applications of isotopes in our daily life. There are 2 types of isotopes, radioactive and non-radioactive isotopes. There are about 2700 isotopes of various elements. All of them are not stable. Let us take an example. Natural carbon is a mixture of 3 isotopes, 2 of which are stable and the third one, carbon-14, is unstable. Nuclei of an unstable isotope undergoes spontaneous change over a period of time. The unstable carbon isotope, carbon-14, emits radiation and changes its nature as a result of neutron changing into a proton. So, it turns into a different element, nitrogen-14. Unstable isotopes which undergo disintegration like this with the emission of radiation are referred to as radioactive. Radioactive isotopes produce harmful radiation. They can have important uses if handled properly. They can be used in medicine, industry, agriculture, archaeology, and the like. Medicinal uses. Gamma rays emitted from cobalt-60 are used in radiotherapy for treatment of cancer. A heart pacemaker which contains plutonium-238 is used to regulate the heartbeat of patients with heart problems. Iodine-131 is used in the treatment of thyroid diseases. For example, the radioisotope iodine-131 is used to diagnose problems in the thyroid gland. The thyroid gland normally absorbs all isotopes of iodine. Therefore, a PET scan on a healthy patient would show the injected iodine-131 to be absorbed by it. However, if the thyroid gland is not functioning properly, the iodine-131 will not appear to be absorbed, showing a cold spot on the imagery. Let us now learn about agricultural applications. The uptake of phosphate and the metabolism of phosphorus by plants can be studied using a phosphate fertilizer containing phosphorus-32. Food irradiation is a method of treating food in order to make it safer to eat and have a longer shelf life. This process is not very different from other treatments such as pesticide application, canning, freezing, and drying. The end result is that the growth of disease-causing microorganisms or those that cause spoilage are slowed or are eliminated altogether. This makes food safer and also keeps it fresh longer. Food irradiated by exposing it to gamma rays of a radioisotope, one that is widely used is cobalt-60. The energy from the gamma ray passing through the food is enough to destroy many disease-causing bacteria as well as those that cause food to spoil, but is not strong enough to change the quality, flavor, or texture of the food. It is important to keep in mind that the food never comes in contact with the radioisotopes and is never at risk of becoming radioactive. Radioactive tracer studies using carbon-14 have helped in the understanding of photosynthesis and protein synthesis. We will now learn about the archaeological uses. Carbon-14 can be used to estimate the age of bone, wood or fossil by measuring the fraction of carbon-14 it contains. Our atmosphere is constantly being bombarded by a stream of energetic particles called cosmic rays. When a cosmic neutron hits the nucleus of nitrogen, the main component of the atmosphere, it transforms into the radioactive carbon isotope C14. This isotope in turn decays, emitting beta radiations with a half-life time of 5,730 years. The balance between the rate at which an isotope is generated by cosmic rays and the rays at which it disappears by radioactive decay maintains the concentration of C14 in the atmosphere at a constant level. The isotope in the form of carbon dioxide is absorbed by plants and indirectly by animals. Therefore, it is assumed that the concentration of C14 isotope in all living organisms is the same as in the atmosphere. When the organism dies, it ceases to exchange carbon with the surroundings. The level of C14 falls gradually as the radioisotope decays. Measuring the amount of C14 in archaeological and paleontological findings allows an estimation of the time when a particular organism died. Industry. Sodium-24 can be used to trace leaks in gas or pipes and ventilating systems. How many of us have smoke detectors in our house? Chances are that a great number of homes have had one or more of these devices installed as an early warning system in case of fire. What most consumers don't know is that many of these units contain a small amount of americium-241. By utilizing the radioactive properties of this material, smoke from a fire can be detected at a very early stage. This early warning capability has saved many lives. In fact, studies have shown that 80% of fire injuries and 80% of fire fatalities occur in homes without smoke detectors.